All right, good morning. Let's start lecture, okay? Okay, so let's continue on the topic that we learned from last lecture. I think I just want to go through an example and before we go on to a new topic. So this is what we learned from previous lecture. We learned how to estimate change using the directional derivative formula, and we also learned how to get the minimum and the maximum for a given multivariable function. So in essence, what we do is we follow two theorems. The first one is called first derivative test theorem. The second one is the second derivative test. It's very much similar to finding the minimum maximum for a function of a single variable. First derivative test for multivariable function, for example, if a function two variable, then what you do is basically you set the gradient of this function to be 0. And that resulted in the two partial derivative fx, fy to be 0. And you let them to be 0, solve for x and y, so because you're going to have two equations, two unknowns. The solution for the x and y are what we call the critical points. But we don't know whether this critical point is a minimum, maximum, or saddle points. So what do? We basically follow the second derivative test. And the second derivative test is a little bit more rules that are here to follow. So there are 1, 2, 3, 4 rules. But you need to calculate the second derivative. Okay, fx, fyy, fxy. Okay, follow the 3, 4 rules that are here, and you'll be able to tell whether it's a minimum, maximum, or saddle point, or inconclusive. So let's take a look at an example for this, applying these two rules that are here. Okay. By the way, some of you asked midterm. I'm not quite finished yet. We're marking over 300 copies. It's quite a challenge. We'll try to finish by Friday. Okay. If not, then definitely next Monday. Okay. So far, I think people are doing pretty good, in my opinion. There's some not so good ones, but in general, you have been doing okay. Alright, so let's take a look at this example here. Given this function f of xy, okay, we want to find all the minimum, maximum, okay, or the saddle point. So at this stage we don't know, right? We just need to find out what type of points, what type of critical point exists for this function. So bearing in mind, in this lecture, so this theory here applies to function two variables. Okay? If you have a function more than two variables, and then there will be a slightly different version of the theories. Okay. So let's apply basically these two theories, okay, to solve this question. Step number 1 is the first derivative test. First derivative test meaning we let del f equal to 0, so gradient to be 0, because at the critical point your gradient value will be 0. And gradient value is 0, meaning there's no increase or decrease at that particular point. And this gives us two expressions. One is fx, one is fy. So partial f over partial x give us 24x squared plus 6y. And the second one, partial f over partial y, give us 3y squared plus 6x. So letting these two equations to be 0. Okay. So typically, at this stage, when you solve these kind of two variable, two equations, okay, unfortunately, you're not going to have two linear equations. So most of the cases you're going to have is two nonlinear equations here. But the substitution rule is always, the fundamental method approach to solve this kind of a set of nonlinear equations. So, for example, from the first one here, you get y equal to negative 4x squared. So then we substitute, okay, this y equal to this, so sub into the second one here, and that gives us 3 times negative 4x squared plus 6x equal to 0. Okay, so this gives us 48x to the power 4 and plus 6x equal to 0. Okay. So take out the common factor x, you get 48x cubed plus 6 equal to 0. Okay. You can cancel a common factor 6, so 8x cubed plus 1 equal to 0. Okay, so that's the final simplest format I think you can get. Okay. Then, in order for this to be 0, either the first one is 0, so x equal to 0, or 8x cubed plus 1 equal to 0, and that gives us x equal to negative 1 over 2. So there are two solutions. Okay. Okay. And by the way, this actually reminds me of marking the first question, because I'm marking the first question and Dr. Klug is marking the second question. The first question, remember asking for the intersection. A lot of you know how to solve, how to use the approach to solve basically intersection point. But many of you actually make a mistake to get the right S value and T value. So I didn't deduct many points. If you make a mistake, you get 1 point deducted. But that does show actually, you need to work very carefully, right, in terms of the computation skill. Okay. A lot of people making mistakes when we move one variable from one side to the other side. There should be a sign change, but a lot of people making that kind of mistake. Okay, so there are two solutions at it here. Then we look at the first one here. If x equal to 0, then what does the corresponding y value is? Basically, we got 2 points, 2 critical points. Now we can substitute x into any one of the equation over here. That gives you y equal to 0. If x equal to negative 1/2, and then substitute, so let's say, into the second one and here, you get y equal to negative 1. Okay. So what this means, basically, we got 2 critical points. The first critical point is 0, 0. The second critical point is negative 1/2 and negative 1. And these 2 critical points, at this stage, we don't know whether they're minimum, maximum, or saddle point. So that's what we're going to do for the second step, which is the second derivative test. To get the second derivative test, if you look at the theory here, right? If you look at the theory, we're going to have to look at the sign of a number of these second-order derivatives. So we need to calculate fxx, fyy, and fxy squared, and then look at the signs and look at the sign of this expression. So let's calculate this expression first. What is fxx? What's fyy? And what's fxy? First, the 3 second-order partial derivatives. Now we already have calculated fx. Okay, so this is fx at here. Fx. All we need to do, this is fx here. We just have to calculate another partial derivative with respect to x using that results. So you get 48x. Similarly, you get this 6y here and 6 at here. Okay. Okay, so that's the 3 second order partial derivatives. Now, because we have 2 critical points at here, so we need to check each one of the critical points separately. Okay? So let's check. This is 0, 0 point first. So 0, 0 point, basically this is your A value, this is your B value at here. Then you substitute this 0, 0 into fx, xy, fyy, and fxy. Okay, so that gives us fx 0, 0 okay, equal to 0 here. Fyy apparently 0. And fxy doesn't matter, it's still 6. Okay, so now you got all 3 numbers, and time to match these numbers, assign the numbers with the theory here. But I guess we need to do one more thing here. What is this value here? So fx times fyy minus fxy squared, because that's the expression we're going to look at the sign. And this calculation gives us negative 36, and negative 36 is less than 0. So let's take a look at this theory number 2. Okay, so if I look at the theory number 2 at here, the only condition has that fx fy minus fxy squared less than 0 is the item number 3, right? So that basically means the point 0, 0 location is a saddle point, according to the second order derivative test. So this one here basically means hence this 0, 0 is a saddle point. Yeah. So that's the idea. Okay, now let's check the second stationary point, negative 1/2 and negative 1. Okay, for this particular point, I can plug in xy here into the 3 second order derivative, and we can get fxx equal to negative 24, and then fxy equal to negative 6. fxy is still 6. Okay, so fxx is less than 0, and then this expression is equal to, if you plug in all the numbers here, it's equal to 108, and that's greater than 0. Okay, so you can put this together here, okay, just for the ease of making a decision. Okay, so then if you have the sign of these 2 expressions now. If you go back to the theory, and which one does that match here? Which is the first one here, right? Yeah. So that means the negative 1/2 and a negative 1 point is a maximum location. Okay, so local maximum. So okay, yeah. So that's the idea of applying the 2 theories here. And often in time, when you get knowledge, okay, if this is a local maximum, then what is the value of the local maximum then, right? And it's very easy. All you need to do is you just have to substitute this value into the original function. So the value of the local maximum equal to original function with the stationary substitute, and I give you a value of 1 at here. Okay, so and I'll show you what this one looks like here. So I think I have a graph in the lecture notes. Yeah. So if you graph out this function fxy, so this is fxy here. If you graph it, and this is how it looks like. It looks like a butterfly. Okay, the wing is a butterfly here. So there are 2 points here. Okay, as you can see, this point is the 0, 0 point, and this point is a -1/2 and -1 point. So this clearly is a local maximum, and this one here is clearly a saddle point here. Now, if you look at this graph, and then you'll see why this is called a local maximum, because as you go this way here, the surface actually keeps going up here, right? Going to infinite. So that's why this is called a local maximum. Okay. So you have this formula. You have this formula in final exam, but I just need you to be very comfortable with how to make a decision by first calculating all those terms that are here. Right? Yeah. So I don't see any really challenge at it here. It's very procedural type of work. Okay. So this is basically how do you get the minimum and the maximum location or saddle point given a surface f of x, y. Okay. Now, for this type of question, okay, we have a word, actually another type of words at here, okay, like this type of question, finding the mean and the max. Okay. We call this is unconstrained here. Okay, unconstrained. So what does unconstrained means basically? If you look at the xy value, right, if you look at this xy value for this surface, we don't have any constraint. The xy value can be moved to anywhere in the xy plane. You can pick any xy value, plug it into this function f at here. Okay. So that's why it's called unconstrained here. And then this time we're going to have a different type of issue at here. Okay. Yeah. So maybe let me just quickly illustrate. So, for example, if I have a surface like this, okay, unconstrained basically means I can pick anywhere in the xy plane, and I will get, okay, so here's the local minimum, here's the local maximum. Okay. So that's unconstrained. However, okay, so this is unconstrained. However, there is another category of problem, which is this. So let's say I have the same, for example, same surface, okay, f of x, y. But this time, the xy value, okay, will not be so lucky, will not be able to be changed, to move around anywhere within the xy plane. So the xy, let's say, actually will be constrained to a trajectory inside this xy plane. So which means your xy here, okay, will be constrained to here. Not going to be here, not going to be here. It's going to have to be here, 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 like this. Okay, so that's called unconstrained. That's called a constraint problem now. So if your xy is constrained to here, as you go along this trajectory, okay, and there will be a certain value corresponding to this surface at here. So the question basically becomes, the next question is, will we be able to find the minimum and maximum location as we're going along this constrained curve at here? Okay. So that's the second category we're going to look at it today. Okay. Basically, we can call it constrained max, mean and max. Okay. For constrained problem. Okay. And we'll introduce a new concept which is called Lagrange multiplier, okay, from this problem in here. Okay. Now, before we formally introduce the approach, okay, which is the Lagrange multiplier, so let's take a look at an example of this constraint problem here, okay, which is actually you probably being able to solve that, okay, in the past. So let's say, suppose you're going to design a fence, okay, and the fence has an area of 1,200 square meters. So this is your constraint basically. And you're going to design, the fence is going to be a rectangular fence. Alright. But unfortunately, what you decided to do is you decided to choose different material for the sides of the fence. So let's say, for example, for this side of fence, if you choose $50 per meter material, okay. But for every other 3 sides, okay, so for the other 3 sides here, and you choose a material a little bit cheaper at $30 per meter. Okay, so you have rectangular fence, so L here and W as the height. Okay. And what you want is, okay, you really want to minimize the cost. So this is a very practical problem here. Okay, so if you're a builder or if you're a contractor, if you want to maximize your profits, then you have to minimize the cost, right? Yeah. So let's take a look at this question here. Basically, what will be the appropriate L and the W value such that you can minimize the cost here? But your area has to be kept at 1,200 square meters. So here's how we're going to approach this question, right? So let's write down how much cost does it require, okay, to build this fence. You got 2L here, 2W here, and we have the cost for each side. So this L is $50, so that's L times 50. Okay, so this is how much cost to build this side here. And this is L, $30 per meter, and you got 2 W's added here times $30 again. Okay, so that's the total cost. A little bit simplification, you get 80L plus 60W. Okay, so if there's no constraint, then this is a total cost here. But there is a constraint though, right? The constraint basically is, here is what we call the constraint here. So the constraint is L times W, which is the area, has to be 1,200 square meters. Okay. So if you look at this curve, this is basically what we call the modeling. You know, you have a question, you model the question into a mathematical expression now. You are trying to minimize these costs, and then the language is subject to the constraint LW equal to 1,200. Okay. So to solve this, we'll have a general approach following this example here, but I think you actually probably tried to solve this question before, which is the following solution using substitution here. So let's say this is a constraint. From the constraint, we can obtain L, which is 1,200 divided by W. Then I'm going to substitute into the cost function, which is 80L plus 60W. So we're going to substitute this L into here. And let's say we call this is C here. The cost is C equal to this 80L plus W. So now C equal 80 times 1,200 over W plus 60W. So now your cost function C, right? Instead of as a function 2 variables, and with the substitution, end up with just one single variable W. And simplify this a little bit here, and you got W at the bottom here, 80 times 1,200 plus 60 W squared. There's a big number here, so I'm going to just let A equal to 80 times 1,200, let B equal to 60, okay, just to simplify my writing it here. So there. So your C, your cost, is simplified into function of single variables now. If I'm going to minimize the cost, okay, then I can treat this function c the same way as I treat the function single variables. So what do? We basically set the derivative of c with respect to the w and set it equal to 0 and solve for stationary points. Right? And let's take a look at this simple question here. If I calculate the derivative of c with respect to w, you can apply the quotient rules to it. Okay? You get basically bw, you're going to get a bw square minus a over omega square. Okay, so set equal to 0, and the only way to for this expression to be 0 is the numerator to be 0, and then that gives you w equal to positive and negative a over b, and you cannot have a negative with a w, so we pick the positive one, the a over b, and a is 80 times 1200 and b is 60, so plugging these two numbers in here and you will get a 40 for the w. As w is 40, that means the L is 30. Yeah. So L turned out to be shorter than w. So that's your solution basically. Okay. If L is 30, W is 40, then you get the minimum cost, okay, for this fence. So that shows you basically a way of solving a constraint problem here using substitution, turning a function of two variables, okay, minimizing function two variables into minimizing function of a single variable here. Okay, so that's something we have learned before, okay. But I'm going to show you actually a different, more formal ways how to basically solve this kind of question here. Now, first, let's formally formulate, okay, this kind of a problem in here. Okay, so let's formally formulate the problem here. Objective. Okay, you all have two things. The first thing is objective. The objective is either maximize or minimize a certain function. So I'm going to always use function two variables to illustrate this idea. So maximize or minimize this function z equal to f of xy. However, you do have a constraint, so subject to a constraint here. Okay, subject to a constraint, and the constraint will be denoted as, okay, g of xy equal to c, and c is a constant. So this is a formal formulation of this constraint problem. You have a function two variable, and you also have a constraint here. Now if you look at the constraint g of xy equal to c, so don't be disguised by by this the look of this function here. Now this essentially is a curve in xy plane, and this is a surface, right, in 3D in the xyz space. Okay. So constraint meaning your x and y will not be anywhere but on this curve g of xy equal to c. Okay. To start this, to start the question before we hear, if you look at some of the famous textbook for optimization, okay, there is basically a very famous problem called the milkmaid problem. So here is this problem. I don't know actually how they generate the problem here, but a lot of people using this one here to start with the introduction of this constraint problem here. So basically, suppose that you have a river over here, and you have a milkmaid starting at this location, okay, M location. So, and the cow is over here. Now, she has the bucket. In order to get the milk, she had to rinse the bucket first, okay, and then get to the cow. Okay. But she does have a more important thing to do. For example, she may be trying to meet one of her handsome boys somewhere, so she had to finish the job as quick as possible, right? So that's basically the milkmaid problem. She has to finish the task, rinse the bucket, and then get to the cow and get the milk. Okay, so that's basically called the milkmaid problem here. So how do we formulate the problem then, right? How do we, this is a very typical example of constraint problem here. Now this river, okay, this river here, we can consider the river as a curve with a certain function g of x, y equal to c. So you can use a certain function to describe the river. Okay? And now the next question basically becomes is, what are we trying to minimize at here, right? As you can see, if she wanted to finish this task as quick as possible, basically means she has to find what? If this is the point P, she has to find the minimum or shortest distance, right? So from here is the distance, from here is the distance, so she has to find the shortest distance from the starting point to the river, and then from the river bank back to the cow. Okay, so now you can formulate the problem here now. How do I minimize a distance? Okay. And in this case here, I'll just call it dist. Okay. And the distance is equal to the distance PM plus PC. Now bear in mind the location of the initial point and finishing point are known, right? So let's call this is XM, YM, and let's call this is XC, YC. So these two locations are given. And P is a general point, so that's your XY location. So now I can, using the given and the unknown, to calculate the distance PM and PC now. So PM, PC, you can calculate, and then this basically the distance, right? It's like a vector, the normal vector here. So that give you x minus xm squared plus y minus ym squared, and then plus the PC, which is x minus xc squared, y minus yc squared. There. So that is the function you're trying to minimize. This is the distance. And subject to, right, don't forget, you do have a constraint here. So subject to this river function, g of xy equal to c. Okay, that's a very interesting question. Okay, but unfortunately, I'm not going to solve this question for now because it's relatively taking more time. So we'll use a simple example to solve here. Okay, but I had to introduce an approach first. But just to give you a thought for those of you who are interested, if you have this kind of distance function here, distance equal to this plus this. Okay, now if you let this whole equation equal to a constant, if you let this whole equation to a constant, then you will see that mathematically this one represents it's an ellipse. So when this whole thing equal to a constant, it's an ellipse equation. The xm, ym, and xc, yc are the so-called two foci of the ellipse. So basically, you can draw an ellipse, okay, by assuming there's basically an ellipse here, okay, and there's this major axis, okay, along here. That's an ellipse equation. It depends on what constant you're letting it equal to. So that ellipse will become either a little bit thinner or a little bit fatter. Okay, right? Yeah. So that's an ellipse equation. Yeah. Now the solution, right? The solution in here mathematically is if you can try an error actually. If you give it different c value here, so that ellipse will expand, or depends on c value. But at a certain point, that ellipse will become what? Will become tangent to that bank of the river. And that tangent point is basically the solution of this minimum distance point. Okay? Yeah. But we wanted to actually give you a more systematic approach here. Okay? Yeah. Okay, so let's try to look at this question here. But I'm going to introduce, in order to do this, we're going to have to introduce a new concept, which is called Lagrange multiplier. I won't explain what Lagrange multiplier yet, but you will see once we're going through the simple procedures. So Lagrange multiplier. So remember, I'll just rewrite our objective here. Okay, is trying to minimize a function. Okay, actually, I'm going to use minimizing for illustration now. Then subject to a constraint g of xy equal to c. Okay, so let's take a look at the approach that we're going to use at here. Okay, I'm going to draw something to illustrate the approach. So here's my favorite surface. Okay, so z equal to f of xy, and we have a certain constraint g of xy equal to c. So I'm going to draw this constraint, okay, inside the xy plane here. So here is our constraint. Okay. So the question basically, we can think of the question basically like this now. I can assume there is some kind of person A, okay, gonna go walk along this constraint curve here. So this guy gonna walk along the constraint curve. At the same time, right? So whenever you're moving along the constraint, so there will be another guy being sort of constrained by the person at the bottom. So if you're here, then there is a point on the top of the person. So if you're here, there will be another point which is corresponding to the surface, and it's basically anywhere. Okay, if you plot it out, okay, so there will be a certain curve. Okay, let's use the red one here. There will be a certain curve, just illustrating here. Okay, you can plot it out along that surface there. Okay, yeah. So this is the person A's trajectory, and this is the person B's trajectory, but that's going to be on the surface z equal to f of xy. Okay. So the idea is basically, if you go along the constraint, and this person B is going along the corresponding curve, another curve on the surface set here, can we find the minimum point? In this case, my drawing here, that will be this location, right? Can we find that location here? So that's basically what we call the minimizing this function as subject to this constraint. Is that good? Okay. So let's make use of what we learned. Make use of what we learned from previous lecture to formulate the problem here. Now first, let's take a look at the constraint g of xy equal to c. Okay. So when you have a function g of xy equal to c, actually that should remind you a little bit When we learn multivariable functions, let's say when you want to learn this, z equal to f of x, y. And one thing I said to illustrate is to plot it out. You get a surface, right? What's the other way to illustrate this surface? Is to what? To use a, do you remember, what do we use again? To use a contour, right? And to use a contour basically means we slice the surface with different z constant. So we let the z equal to c, and then we get f of x, y equal to c. Okay? Yeah. So this guy here, f of x, y equal to c. Now if you think backwards, if I give you, instead of x, y, f here, let's see g. If I give you g of x, y equal to c, okay? Now you can also think of what? You can also think of as a level curve of a certain surface, g of x, z equal to g of x, y. That makes sense, right? So this is a curve, but you can always think of a level curve of another surface, z equal to g of x, y. Okay. So bottom line here is, I wanted to say this is a curve, okay? And more precisely, you can also consider it a level curve. Okay? So level curve for another function, for example, w, let's use the w here, equal to g of x, y. Okay, so that's something I want you to bear in mind for now. Okay, that's number one. And second of all, okay, I can, given the function g of x, y, I can calculate the gradient del g. I always calculate the gradient del g at here. And given this constraint curve, and given the guy is walking along the constraint here, then at any location, right, at any location here, I can consider a tangent vector u hat as the direction of moving. So if I draw a tangent vector at this location, the u hat, and using the unit vector u hat to represent a tangent vector, and that will be the direction of moving. This is now basically coming into a concept called the directional derivative now. So u hat, okay, is a tangent vector to this curve. Okay. And it is also the direction. It is also the direction of the moving points. Yeah. So we're breaking down into the details here. Okay. So here you have a u hat and you have a del g. Now back to the previous lecture. When we calculate del g, this del g, apparently this is a function two variable. So when you calculate del g, the end of the gradient vector, which is what? It's a vector in the 2D space. Now if you recall that, the gradient vector must be one of the properties we learned. This gradient vector del g must be what? The del g and the u hat must be perpendicular. Okay, if you recall that. So del g is perpendicular to the level curve, or del g is perpendicular to the tangent line or vector at that point. Right? If you recall, that's one of the properties we introduced. Okay? So this is basically going to be our number one fact. So here's going to be our fact number one. It's that del g perpendicular to u hat. So this fact is irrespective of the current current constraint problem. Okay. It's a nature. Basically, whenever you have a curve, okay, and it's a level curve of function w equal to g of x, y, then del g must be perpendicular to the u hat. So there's second fact, but it is going to take a little bit of explaining and here again. Okay. The second fact comes from the directional derivative So recall the directional derivative formula is df over ds u hat equal to del f dot u hat. So that's the formula for directional derivative. Okay. So before we move ahead, so let's recall what does the directional derivative actually means, right? If you recall that directional derivative basically means you have a function f. If you're changing your x and y in the direction given by the u hat, then what will be the rate of change of this function f, okay, by a small after the small displacement as said here. So this essentially gives you the rate of change for, and as a matter of fact, maybe before I write it down here, so just a quick reminder here. I'll use that very simple function, right? So if I have a z equal to x squared plus y squared, if I move in the direction of I hat direction, right, this is I hat direction. For example, this is just a y equal to 2. Then if you recall that, then what happens is you're going to have a curve, okay, traced out, okay, on that surface, z equal to x squared plus y squared paraboloid. So basically you're going this way here, right? Like this, as you're moving in this direction, okay, as you're moving direction here. So directional derivative basically means what will be the slope or rate of change for this red curve at here. So the conclusion at here is the rate of change for the curve, which is this curve here, okay, traced out on the surface when there is a change in u hat direction. So rate of change, it's basically slope concept. Okay, so that's directional derivative concept. Okay, so apparently if you look at this, if you relate this rate of change or slope concept to function single variables, then there is a situation that this rate of change is 0, right? It could be the directional derivative become a 0 value here. Okay. Then what does this 0 value means then, right? So if you look at this expression here, or the idea of the rate of change at here. So when the df over ds equal to 0, at least from here, I can see what? It must be where? It must be at this local minimum location at here. Okay. Yeah. So the df equal to 0 here, there's no change. So when this is 0, then at that location, okay, no change in f. Okay, so there's no change in f at here. So that's basically what directional derivative equal to 0 means. Now getting back to the directional derivative formula here, if the left side equal to 0, then the del f dot u hat equal to 0. So that gives you del f dot u hat equal to 0. And this is basically means, but not always 0, right? So this equal to 0 at that critical location. Okay. So now you see, this is basically our second fact at here. Okay, the second fact. This is a special relationship. And this relationship is only satisfied. Okay, it's only satisfied when the directional derivative equal to 0. And that equal to 0 means we are at a local minimum location. Okay? Yeah. That's it. So this equal to 0, as we learned from the simple dot product, meaning the del of f must be perpendicular to the u hat, right? So if I get back to this graph right here, okay, get back to the graph. So I want you to visualize, okay, actually I'm going to show you a maple. This hand drawing won't be very good. This is the surface at here. If I want to draw del f, okay, so if I want to draw del f for this surface, given this function here at any arbitrary point, what do? I basically calculate the partial derivative, right, and plug in the coordinates of the point into the del f. Okay. So literally at any location as this person A is moving along the curve C, you could always draw a grading vector del f. Okay? You can always draw a grading vector at that location. And this grading vector will be perpendicular to the level curve of this surface, which I didn't draw it here, right? Okay. Now, so which means at any point along that constraint, you always have 3 vectors. So 1, 2, 3. In general, you always have 3 vectors. Del G is always perpendicular to u hat. But at this particular location, okay, at this particular location, which is the local minimum, then you have u hat, you have del G, and you also have a del F. So now the del F, guess what? Is also perpendicular to the u hat. Right? That's the nature of the local minimum there. Right? So at that local minimum here, this is your relationship, okay, between the 3 vectors. And basically is what I have written down, okay, for the 2 facts, factor 1 and fact number 2. So factor 1 is this. Factor number 2 is this when we're at the local minimum. So mathematically, when you have this relationship, what does it prove? The del G must be parallel to this del F vector here. Right, so if you look at this graph here, del F, in this way I draw it here, but it could be pointing the other way, not giving any functions. But okay, the del F and the del G, they must be perpendicular at this local minimum location. So this one here at the local minimum, okay, or maximum, yeah, the critical location. So let's just call it critical. Okay, yeah. Okay, so this is the conclusion, simple conclusion actually, after we have gone through this constraint problem here. The 2 vectors has to be parallel to each other. So mathematically, when you have 2 vectors are parallel to each other, they are essentially going to be what? Different by a scale. So we introduce a lambda scale, okay, to represent this relationship. Now, for conventional writing here, we write a negative in the front. Okay. It really doesn't matter, you know. This is just for the ease of writing here. It's just a scale. It's just constant, right? So the negative can be always incorporated into that constant lambda. Okay. So now we have this simple relationship, okay, and the lambda at here is what we call Lagrange. I don't think there's an E here. There is an E here. Lagrange multiplier. Okay. So this lambda is called Lagrange multiplier. So very famous name, you know. Essentially, there's a French called Lagrange, and if you go to the Eiffel Tower, his name is actually etched on the Eiffel Tower. So we solve this basically constraint problem based on this relationship. Okay, yeah. So let's starting from here. So what is del f then? Is partial f partial x, partial f partial y, right? Okay. And what's the del g? It's partial g over partial x, partial g over partial y. Okay. So to write it out, you get basically this expression here. The left equal to the right, okay, meaning the components of the vector has to be the same. So that gives us partial f over partial x equal to negative lambda, okay, times partial g partial x, and then partial f partial y equal to negative lambda partial g partial y. Okay. Yeah. So I'm gonna move everything to the left side, and we get partial f over partial x plus lambda partial g partial x equal to 0, and then partial f partial y plus lambda partial g partial y equal to 0. Okay. Now this is the two equations. Yeah. Now f of x y is function two variables. G of x y is a function two variables. If you have the two functions, you calculate the two partial derivatives, and you put it in here, right? So basically, up to here, you got two equations. How many unknowns? You have xy here, and you also have a lambda here. So two equations, three unknowns, right? That you cannot solve. In order to solve, you need a third equation. So what would be the third equation? There's one we haven't used yet. What will be the third equation here? What's the nature of the problem, remember? It's minimize this subject to this, right? That's the third equation here. So okay. So you have three equations, three unknowns, and then you will be able to solve for a solution x, y, lambda. Is that good? Yeah. So in basically, in simple language, that after all the derivation, when you have a constraint problem, all you need to do is to formulate the problem into 1, 2, 3 equations at here. And solve for x, y, lambda. The solution is what we call the critical location. Okay, so this is basically the critical location. Okay. Now you have a question basically, is that location minimum location, maximum location, or saddle points, right? Yeah, could be. Now that requires higher order test, but that's kind of out of the scope of this lecture now. Now in our class, okay, what we often deal with, okay, that's actually a very specific type of function. For example, I'll give you a function like this. Okay, so I'll give you a surface f of xy equal to x squared plus y squared. So you know what this surface looks like. It's a surface where it's a bow always pointing upwards, right? Yeah. And it's just like the drawing at here. So which basically means really doesn't matter what kind of curve you choose in the xy plane, and all of the corresponding curve going traced out on this surface will always have this kind of a shape, which is basically upward here, what we call concaving up. Okay, yeah. So that's called a convex actually kind of curve, and in this kind of curve, as you can imagine, you will always have what? A local minimum like this. Okay, so in our case, we sometimes have a specific wording, basically try to minimize, for example, minimize this function subject to a certain constraint. So the reason we can see minimize is because the curve is a special one, is concaving up here. Okay, yeah. So it's called a convex optimization in here. Okay. All right. So let's take a look at it. Before I take a look example here, I really wanted to actually another one here, a little bit of variation in here. Okay. So the variation of this Lagrange multiplier. So the variation in here is we're going to define a new function. Okay. Let's call it L. Okay. So this L equal to f of xy plus lambda and then g of xy minus c. So we define a new function here. Okay. As you can see, the function we defined, okay, actually consists of all the given functions. It has the given function f of xy. It also has the given function g of xy, and it also has this Lagrange multiplier lambda. Yeah. Now this function has a name. It's called Lagrangian function. Okay, it's called the Lagrangian. Yeah. When I teach a fourth year digital control course, and we have a chapter basically on optimal control, and in that chapter we use a state space model, basically not just a simple scalar function in here, but we use exactly actually this kind of Lagrangian in here for derivation of the results of that optimal control method. Okay, so it's directly related to this concept here. Okay. So what's so special about this new function L then, right? New function L. So if I just, let's say, forget about everything, I just say, here's the function L, and I want you to minimize or maximize this function L. Okay. So what would you do if you wanted? Here's the function L, and I wanted you to minimize and maximize this function L. So what's the first step you would do? What would be the first step? First derivative test. First derivative test meaning calculating what? That's right. Basically, you calculate the gradient, right? And then set it equal to 0. Okay? Yeah. So that's, if you forget about everything, if you have this one here, and then that's what you do, right? So let's take a look at what does this gradient L equal to 0 give us then. Okay. Partial L over partial x. Okay, so here's the L here. Give us partial f partial x plus lambda times partial g over partial x. So that gives you 0. And the partial x partial y will be this one here. And then partial L partial lambda give us g of xy minus c, and then equal to 0. So if you calculate the partial derivative, okay, each one of them, and then set equal to 0, so this is what you get for the first derivative test. Okay, yeah. And if you look carefully of the results that are here, this is actually what? This is actually exactly what we have just written down for the 3 equations that are here, right? Yeah. So that's the beauty of this new function Lagrangian. And the previous formulation is a constraint problem. Now the Lagrangian actually becomes what? Unconstrained problem, right? Yeah. So that's basically a shift of perspective, okay, from constraint to a non-constraint here. You don't really have to memorize this section here, but my expectation is you're going to have to be able to know this here, okay, in order to solve a question. Okay. All right, so let's take a look at an example before we can call it a day. Any questions so far? Yeah, it's a lot of writing. Okay. So I'll use two examples that are here. Okay. Actually, let's try this first one here. So f of xy equal to x squared plus y squared. Okay, so minimize this function and then subject to g of xy equal to x times y and equal to 3. Alright. Okay. So let's follow the procedures to solve, and then if I got a time, I will demonstrate to you using the maple just to see what exactly we're looking at it here. Okay, so we have three equations, need to formulate first and then solve. First one is partial f partial x, okay, plus lambda partial g over partial x equal to 0. So let's take a look at what will we get, okay, for this expression. Here's function f. Its partial derivative with respect to x is 2x. Then here is the partial g over partial x, so this is xy, so that gives you y here. Okay, that's the first equation. And then partial f over partial y here's 2y plus lambda times x equal to 0. So second equation here. And the third equation is a constraint, so xy equal to 3. There. So three equations, three unknowns, and we'll try to solve it now. Okay. So let's take a look at the solution, right, for this one and here. They're different. Now from here, I can see a lot of people probably try the different type of methods. There's different ways of solving it. Substitution is always one approach, straightforward approach. But sometimes substitution actually, and one example actually in assignments, I think, forgot this is this week assignment or next week assignment. Direct substitution may not work very well from the beginning. Okay, but for this one it will work. Okay. So here's what I would do. This is one of the methods here. Let's see, from number one equation we can get lambda equal to negative 2x over y. So lambda equal to 2x over y negative. So substitution doesn't necessarily always substitute lambda into other equations. Sometimes you substitute x, or sometimes you substitute y. Right? So I'm going to substitute into, let's say, equation number 2. Okay. So sub this lambda into equation number 2. So that gives us 2y minus 2x over y times x equal to 0. And to simplify this, so you can multiply the y here. So there's 2x squared, 2y squared. So overall you get x squared equal to y squared. So x squared equal to y squared mathematically means what? X equal to negative y or x equal to positive y. Okay, so that's the x squared equal to y squared. So we don't have a solution yet, but we've got a relationship between x and y. Okay. So now let's try either one of these at either one of the case. So if we have x equal to negative y, so we can plug it into the third equation. That gives us negative y cubed equal to 3. Okay. And is that possible? That's not possible, right? So y squared is always a positive number, so you cannot have a negative positive number become 3. So that's basically impossible. Okay, so x cannot be negative y. Then we have only this x equal to y relationship, right? And that gives us y squared or x squared equal to 3, doesn't matter. So that gives us x squared equal to 3, or x equal to positive and negative root 3. So x has two values. If x is positive root 3, then the y is also positive root 3. If x is negative root 3, then y is a negative root 3. Okay, so you got basically here you got 2 points, okay, 2 critical points at here. One is at this location, and one is at this location. And you can also calculate the lambda for either one of the pair of x, y here. Your lambda will always be 2. So you can substitute x or y here into the equation 1 and 2. You can solve. You get lambda equal to 2. Okay. So now you got the solution. So 2 locations and 1 lambda value. More often at this stage, you don't really care about the lambda value. So what you really care is x. Yes.
If x equals to y, would the lambda be negative?
Oh, negative 2? Is that right? So let's double check here. So if I plug 2 root 3 here, root 3 here, yeah, you're right. It's negative 2. Yes, absolutely. Thank you. Negative 2. Very good. So the next logic question basically is, I have 2 locations, then what are the values, corresponding values of the function, right, at the 2 locations? So we can calculate f value at root 3, and we also want to calculate f value at negative root 3, and they turn out both of them equal to 6. Both of them equal to 6. Okay, so basically that means, okay, we have the 2 locations yield the same minimum value, which is a 6. So now this is very mathematical, right? So I have no visualization of what this looks like. So I think I really wanted to show you what is going on here actually. So I want to show you an animation in here. Let me see. So this is the one here. So let's see. Here's the surface, right? This is the surface in our example here. And here's the constraint, x times y equal to 3. Here are the 2 grading vectors. Yeah. And this is the surface. Okay, so this is the surface at here. Number of things just to point it out here is the red one is the level curve of this of the given surface, okay, and the blue one is actually a special one here. You will see that. And then this red one here is the curve xy equal to 3. Now, if I look at it down from xy plane, what is the curve of xy equal to 3? It's what? It's one is over here and the other is over here, right? Yeah. That's the curve xy equal to 3. It's the parabola type of curve. Okay. But in this case, I only draw one here. But then you can imagine there should be what? There should be another one on the other side of the quadrant. Okay, on the other one here. Okay. Yeah. So the point here is basically I'm going to move this point along this constraint, right? And then for every point on the constraint, there will be a point on that given surface. There are two vectors also plotted out. The red vector is the grading vector for the level curve xy equal to 3. As you can see, the red one here is perpendicular to this xy equal to 3. The blue one is the level curve to the blue one is the grading vector to the level curve of this given surface, which is a paraboloid, right? So you can see this blue one is actually perpendicular to the level curve of the given surface. Okay, yeah. So if I'm gonna manually move it along here, okay, as you can see here, this drawing, I didn't draw the frame, but you can literally see that point, that the dot on the top, right, is moving along the surface. It's going to trace out a curve along the surface. And can you tell me at which location is the local minimum? You can see here, that's basically this location here, right? What's the nature at this local minimum location? Look at the two vectors, the red vector and the blue vector for the two grading vector, and they happen to be parallel to each other, right? Yeah. So that basically is the foundation where we derive our the three equations here. So this one here, I think, give you all the dots. So give you all the dots out, and also give you, basically all of the grading vectors at here. Okay. And one more thing I also want you to observe. Okay, let me see which one would be better. Yeah, let's observe this one here. So I want you to observe the level curve. Okay, so observe this blue one here. The blue one is the level curve for the given surface, the paraboloid. Okay, so if you have a point at here, you go up, then you have a level curve, right? Yeah. So watch that blue curve and the constraint when we are at the local minimum. Here's the local minimum. What happened to the blue curve and constraint? They become what? Become tangent. Okay? Yeah, they become tangent here. It's actually, you can quickly prove it. If del F and del G are parallel and they are both perpendicular to the U hat, and that will show you that these two curves will become tangent at this location at here. Okay? Yeah. So that's another nature of this basically constraint problem here. So the level curve of this function that you're trying to minimize will become tangent to the constraint curve at the local critical location, local mean or local max. Okay, yeah. So I think that's if you want, I'll post this one here. You can play around this maple here. Okay, any computer has a maple on the campus. But in essence, what you need to follow is the three equations that are here, okay, to solve properly for x, y, and lambda. Okay, any questions? Okay, thank you.
Great.